Hello everyone, we will move to the next part of our electronic devices syllabus, which is the PN junction. Now as we move forward, let's see that what we have now up to now, what we have done. We have finished that, we have seen that what are the categories of the materials. We will see that what are the properties of semiconductor and how semiconductor is very much beneficial for our engineering purposes, like to manufacture different devices. We will because you can change the electric conductivity of you can modify the electrical conductivity of a material. So you can make marvelous devices using these material which has not been happened. Then we will see that how the internal behavior of a semiconductor work, like how the energy band diagram has been formed and what the purpose of forming an energy band diagram. On the basis of energy band diagram, how will we categorize the semiconductor? So these are the things that we have accomplished up to now. Now moving towards the how you can make a application of semiconductor devices. Now for the application, we already know the biggest application of the semiconductor device is the manufacturing of a diode, which is a very small level device, which small scale device which we used for we all have been using the diode in some or other way, or you can use a diode, or we can use diode for led is also a type of diode, like then we have IR sensors using a diode, photodiode and LEDs. So basically we will the what we call the base element, the base device of a semiconductor is a diode, or in engineering terms we will say it as a PN junction. Now moving to the how we will create a PN junction. Now PN junction has been created by combining the P type of material, P type semiconductor material with the N type semiconductor material. Now as you already know, we have completed in unit 1 what is the P material and a M material. If you dope a semiconductor with a group 3 elements like boron, aluminium, then the material that has been resultant is called P type of semiconductor, which has the majority carrier as holes, and the N type semiconductor material is the material which has been formed with doping of group 5 elements like phosphorus, arsenic. These are the elements which have the 5 electrons in the valence orbit. So they will used as used as a doping element in doping material in a semiconductor, and the majority charge carriers will be the electrons. So you see that in P type semiconductor the majority carriers are holes, and in N type semiconductor the majority carriers are electrons. So it means what is the majority carrier means there are large number of holes present in a P type semiconductor material and large number of electrons present in a N type semiconductor material. But if we combine both materials, suppose we combine both material, not combining like that, combining means during the formation if we combine at the basic level. During the manufacturing, we will combine the P type material with the N type material. Then there is a device form which is called PN junction. Now PN junction has been formed is like that if we combine, like this is a P material. P materials have suppose so many holes. So many holes means positive charge. There is a positive charge available here, positive charge available here. It has combined. This is a P side. Now it has been combined with the what we call with the N side. If we form, this is N side. N side have so many electrons, so many electrons, so many electrons, so many electrons, so many electrons. Now as the electrons and holes are combined, so as the electrostatic force, the normal electrostatic or normal attraction force, the electrons will start moving towards this and the holes moving towards this, and they will start recombining so fast. Okay, as they start recombining, what will happen at the point of intersection. At the point of intersection, there are so many combination occur that at this point, since the electrons combine with the holes and the holes will combine by moving towards this part. Okay, so they will combine, it will provide what we call a space charged with negative ions. Negative ions is what? Because as p material is doped, what we have, the doping element is Na. Na is what? The doping element of A side. Now the ions of Na, because as the Na is what? The acceptor ions. Acceptor ions means it has the tendency to accept one more electron. It is a tendency to accept one more electrons to fulfill the to form the octet, to fulfill that bonding condition, to become a stable or some which we have studied in physics. So the acceptor ion has the charge property as negative, and the donor ion has a charge property as positive. Donor ions means it can supply electrons. It can supply extra electrons. So it is a donor atom. So as the acceptor atom has a tendency to accept electrons. So accepting electrons means accepting a negative charge. So the charge conductivity or the charge polarity of acceptor ion is negative, and the charge probability of donor ion is positive. So at they recombine, there is a time which will occur, due to which in this region we have only the ions are present. Okay, only the ions are present. Ions means here at the edge of p side we have acceptor ions. So acceptor ions has a what charge capability as negative, and the donor side, like in the n side, we have donor ion, which is a charge conductivity as positive. Now as this is positive charge conductivity, this is a negative charge conductivity, they provide a solid wall, solid charge barrier, so that no more holes will pass through this barrier to go this side, and no electrons from this side, from n side, have the capability or energy so that they can move, they can resist, sorry, they can go through this barrier to move towards the p side. So since there is a barrier is created, so that this region is also known as what we call a potential barrier. Potential barrier, or we call it a transition region, because there is a transition of electrons and holes occur. So transition region, or we also call it depletion region. There are so many names. There are so many names present. Okay, so it can be called as a potential barrier, it can be called as a transition region, it can be called as a depletion region. So this is called a potential barrier, or a depletion region, or a transition region. What we see that it has a middle point. Okay, this is called junction. This is called a potential junction or transition junction at the middle of depletion region. At the middle of depletion region is known as junction, and as we move towards the p side in the junction, in the potential barrier, we have negative ions, and as we move towards the n side of N region, towards N region we have positive ions. Okay, so this is what we call unbiased PN junction. Means we have not applied any external electric field or external voltage to this region until now. Okay, now suppose if we apply some potential, suppose we have applied a negative potential to the N side and the positive potential to the P side. Now this is called a forward biasing. Why forward biasing? Because P side is positive, as we assume, we not assume it is a positive, because the majority carriers are holes, and holes conductivity of the polarity or the conductive charge of holes is positive, and the conductive charge of electron is negative. So if we apply a negative of external voltage or external power supply, whatever we call, the negative side is connected to the N side and the positive side will be connected to the P side. This is called a forward bias of PN junction. Now in the forward bias of PN junction, what will occur? Now they have the external force available. Okay, so as this is the positive supply, now the electrons will flow from this side, flow of electron will flow from this side, and from this side they will exert some force, okay, and from this side the hole will move towards this side, holes, and they will exert some force here. As the holes from P side exert some force because they get energy from the power from the external battery, and the electrons in the N region get the energy from the negative side of the battery. Due to this force, the depletion region will constrict and the width of the depletion region will be decreases. So they will exert force here, they will exert force here, and the depletion region will depleted. As you increase the battery, as you increase the polarity of battery, these these depletion rays become more and more constrict, and at some point what will happen, the depletion region will be gone and the current start flowing in this direction. Okay, so this is what we call forward biasing of a PN junction. Then in the reverse biasing, what will happen, we will connect the negative side of a battery with the P side and the positive side of a battery to the N side. Now if we do this, what will happen, the holes from this side will come attracted toward the negative part, and the electron from this region will attracted toward the positive polarity and combined with the positive side. So what will happen, the depletion region will increases, it will contain increase as we increases the polarity of a battery, the value of the as you increases the polarity of a battery, it will the width of a depletion region will be increases. So this is what we call the reverse biasing of a PN junction. So in forward biasing, what we have, the positive supply will be connected to the P type P region, and the negative supply of a battery will connected to the N region. And in a reverse biasing, the negative side of a battery will connected to the P region, and the positive side of a battery will connected to the N region. Okay. Now, since as we see, the potential difference will be highly depending upon what we call the potential difference in between the region. So we have a formula which is what we call a PN junction formula, in which that this is the contact potential, that is the potential difference, built-in potential difference created by the electric field, is given by that Vt. Vt is the thermal voltage. Vt is equals to Kt by Q, or it is at normal at room temperature. What its value at room temperature? Its value is what? 26 millivolt. Then ln nt, V naught is Vt into ln Nd is the donor ion and Na is the acceptor ion upon Ni square, that is the intrinsic carrier concentration. Okay, so this is the formula for the zero bias junction voltage. Means zero bias means when you have not applied any external power supply or external voltage to the PN junction, then some contact potential, because there is a potential barrier. Barrier means some ions are present in that region, and that region has some potential, and that potential is called, we call zero bias junction voltage or contact potential. So that value will be depending upon the doping of P region, the doping concentration of P region and the N region divided by the intrinsic carrier concentration of the PN junction of a semiconductor. Okay, so this is what we call the VI characteristic of a PN diode. Means as you apply a forward bias, the current has not been start flowing through the PN junction. As soon as the voltage is applied, it will take some time. And at what we call at knee voltage. It is what we call at knee voltage. At knee voltage, it will start flowing. The current will start flowing and will suddenly increases. As soon as the reverse biasing has been done, what we have, as soon as the reverse, there is some potential is different, but as you apply more and more negative voltage, there is a point at which the PN junction breakdown has been occurred. Means the current will suddenly there is an abrupt flow of current, and there is no potential barrier has been established in the with the PN junction, and the what we call the diode has been broken, or we call the diode has been heat up. Okay, it was damaged. So there are some diodes which will work on a breakdown. Like we already know, the Zener diode has been work on a breakdown in breakdown region also, because it has been manufacturing like that. But in normal PN diode, if you apply a more and more voltage, it will burn. Okay, it is called a reverse. It will call a breakdown. So, what are the application of PN junction diode? The PN junction diode can be used in a photodiode, as a photodiode is sensitive to the light. When a configuration of diode is reverse biased, okay. It can be used in a solar cell, and when diode is forward biased, we can use as a LED, and it can be also used in a rectifiers, as we see the full wave rectifier and half wave rectifier, in voltage control oscillators, or in vector diodes. Okay, so or you can use it as a in what we call clamper circuits and clipper circuits. So there are many application of diodes. Now, if moving towards what is the basically inside the potential barrier. Now, basically inside a potential barrier, as you know, I already told you, there is some charge is present. It is not like charge is zero. The current, when you have not applied any external field, it is a no bias condition. No bias condition. During a no bias condition means as you have not applied any external electric field or external voltage in a PN junction, there are some charges present in a potential barrier, like donor ions and acceptor ions. So some charge is present, and due to that charge, what we have, since we have to maintain the charge polarity, we have to maintain that the current will not flow in no bias condition through a PN junction diode. In a diode, if you apply a supply, then there is no current flowing, right? So we have to obey that law. So to obey that law, if you have some like potential bit is like the junction is not in the middle, okay, and we have in this region up to the depletion region is up to this point, that is x0 point, and in the P region it is like minus xp point. If we see that it is a 0, x is equals to 0. If we assume it, Okay, not it is like negative or positive. We assume it the middle of the or what we call the junction as a x is equals to 0 point, and as we move towards the right side it is positive, and if we move towards the left side it is negative. Then in the n region it is up to x naught, and in it is in p region it is up to xp naught. Okay, since we see that in the n region at the side of the n region, at the edge of n region, we have positive ions, so the polarity of that region is positive. This is the space charge region, and the negative side in the p side we have negative, but we have to obey the law. So the space charge quantity, it is at this side is minus q ax p naught, and a has been equals to, it has been equal to, because as the charge is more, so area will be less. Okay, so this is what a into a is something like, okay, a, sorry, if we erase this, I will erase this. So it is like we have to obey the principle. It is like minus q a x p naught into na is equals to q a x and not and d. Okay, so this is the space charge region which should be equal to provide no current flow, so that the no current flow through the PN junction diode at no bias condition. And this is the, if we see the electric field, because there is charge, some charge is present, so obviously there is an electric field also present, but electric field is what, it is a maximum, because the potential has been increases from this side to this side. This is the graph of the contact potential. So at the edge of, as the transition at the junction, the transition is maximum. Since Ex is what? Ex is what? Minus dVx upon dx. Okay, Vx, where Vx is what? Potential. So as the potential, there is a change in potential as we going from the P region to N region. So as the potential is maximum, the transition is maximum in the middle, the maximum electric field has been at the junction. Okay, at the junction, and as soon as it will go towards the N region, it will again going to 0. So at the edge of the transition region, the electric field is 0. But in the middle or at the junction, at the point of junction, the electric field is always maximum. Okay, and its value is 1 upon epsilon q into Na. D epsilon d. This is something where we have actually seen in last unit. Okay, so if you want to calculate the electric field distribution in this region, what we have to do, we will use the Poisson equation, which is d epsilon x means change of the electric field with respect to the distance, that is equals to q by epsilon p minus n. P is the hole concentration, n is the electron concentration, and number of holes, number of electrons, and Nd is charge carrier, donor ions, and Na is acceptor ions. Now d epsilon by dx for in, this is for N region and this is for P region. Okay, so for P region, since we consider it is negative, so it will be minus q by epsilon into Na, and in N region it will q by epsilon into Nd. But as we plot, as we apply the limit to that this formula, that is the electric field is in the N region, it is from the from maximum to 0, right? In the if we see this is for in N region, it is from epsilon to 0, and for P region it is 0 to epsilon naught. Okay, so sorry, not epsilon, E naught. So this is for n region, it is the limit of electric field is from E naught to 0, and the limit of the distance is from 0 to x naught. And for the P region, the electric field is from 0 to E naught, and the distance is from xp naught to minus xp naught to 0. So if we apply this limit, and we will get this result, which is equal. And if we, it is simple to relate. Now we, I know that electric field is what? Change in potential with respect to the distance. Okay. So if we apply this formula, and we will see, we will know that V naught is what? V naught is the contact potential, and it is from minus p xp naught to xn naught. Okay, from x minus xn naught to minus xp naught to xn naught, we have the contact potential, as we already know. So we will apply the change in electric field from minus xp naught to in the transition region. Okay, if we apply this, and also we know that a contact potential will be what we call the width of the depletion region is W, and what is the width? It is what? X and naught plus xp naught, which is also equals to W. Okay, so this is how we will solve. This is the final. We got the relation between the width of the potential barrier with respect to the charge density inside a potential barrier. Thank you.